about how we can use quasars as standard candles and to extend the Hubble diagram at high redshift. I'm a PhD student at the University of Florence, and these are the people I've been mainly working on in the past few years, so I just want to show their faces before moving on. So, okay, the Hubble diagram, we'll know it here. Why do we like it? Because if we have enough object to build the distant redshift relation, we can then use the shape of this diagram to test cosmological models, or inside a given model to put constraints on the cosmological parameters. And the Hubble diagram I'm showing you here is the one with Supernovae Ia, which are obviously the most famous standard candles out there. And with them, we can reach redshift a bit higher than 1, which means we can investigate basically the expansion history of the universe up to when it was around 5 billion years old. However, we do not really have supernovae at redshifts higher than that for the moment, so we really would like to have a standard candle at higher redshift so that we can test cosmological models even in the first billion years of the universe. This is when quasars can come in hand, and they're a very good candidate for being standard candles in the sense that we observe them at all redshifts up until when the universe was less than 1 billion years old. And they're also very numerous, which is a nice property to have for something that we want to use as a standard candle. Sad news is that they're not standard. Their volumetric luminosity can vary up to many orders of magnitude. So obviously, if we have a flux measurement of a quasar, we have no idea how distant it is. However, there's an observational result that can help us here. And this is the existence of a nonlinear relation between the X-ray and UV emission of quasars. This is usually parameterized as a linear relation in the logarithmic space, as I'm showing here, with the slope gamma and its normalization beta. I just said this is an observational result because the physics behind it is still something not really clear. We know that the UV emission comes from the accretion disk around the quasar, and we know that the X-ray emission comes from the X-ray corona. And we also know that there must be some kind of link between these two, because something must be refueling the corona with energy, otherwise we wouldn't have persistent X-ray emission. But why, how this link works and why it's not so clear. However, this relation exists, and given that, we can use it to measure distances, because it's clear that if we substitute the flux luminosity relation, we can derive an equation for the luminosity distance only using the relation parameters and the X-ray and UV fluxes. Now, this thing has been known since decades, so it's nothing really new here, but it had not been implemented in cosmology because of the very high observed dispersion. You can see here the gray sample is a sample of 7,000 quasars, and considering this is a log-log scale, you can see how big the scatter is. We usually parameterize it as this dispersion parameter delta, which here is 0.4 depth, so too big to do anything with it. However, it has been shown that most part of the dispersion is not intrinsic to the relation itself, but is due to observational stuff that we can remove in most part if we select our quasar sample accordingly, which means removing objects that might be affected by dust reddening, by gas absorption, or that may suffer the Eddington bias in the X-rays. In doing so, for this sample, we go from the gray to the yellow points, and you see the relation gets much tighter with a dispersion of 0.24. For this blue subsample here, I will not go into detail, but it's a subsample for which you have pointed X-ray observation and very good quality data. We even get lower to 0.12. So this is enough to do some cosmology with it. And so the one I'm showing you here is the resulting Hubble diagram with cyan points here are Supernovae Ia, and the yellow and blue points are the same as before. The red points are the average for quasars in small redshift beams. So first thing, you see how much we can extend this diagram in terms of redshift and therefore in terms of the age of the universe. And the other thing to notice here is that the dashed magenta line is the prediction of the Hubble diagram for a flat ΛCDM model, while the black line is the best fit for supernovae and quasars together. So there's actually a 4 sigma tension between the two, which starts building around redshift 1 point something. and that you cannot really see if you look at the yellow points, but if you look at the averages, you see that they are systematically lower than the ΛCDM prediction. Now, given this, there are so many questions we can ask in terms of, do we believe this tension here? And so what I want to discuss today with you are some of these questions, and because I'm an observational astrophysicist, I declare it. The thing we will discuss now are analyses we have been performed in which they are cosmology independent, and we have been trying to answer these questions in terms of, first, can we trust this tension, and also, can we do something for this dispersion in terms of, can we further lower it, and can we get to understand how much the intrinsic dispersion of this relation is. So, first question, very important thing, does this relation that we're using evolve with the redshift? Because obviously, if it does, we cannot put objects at different redshifts together. We can test this by dividing our sample in small redshift bins. And in each redshift bin, obviously, the difference between distances in object is negligible. And so we can use the relation with fluxes instead of luminosities. So we are not assuming any cosmology here. And if we do so, you see the results for the slope parameter here. What we get is that there is no clear trend with the redshift for the slope, with an average of around 0.6, that is more or less always the same. And you see also here for the dispersion, but this is not as important as the slope. In terms of the beta parameter here, this is actually a calibration parameter. So because we do not know the physics behind the relation, we cannot determine it basically unless we calibrate our quasars with something else. But this is easily done in the sense that we have the common redshift range with Supernovae Ia. And you can see here what we do is basically we match the height of the quasar Hubble diagram with the red points with the one of Supernovae Ia. And once we select the cross-correlation parameter, you see that they overlap perfectly, which also reassures us that this beta parameter is also not evolving with the redshift. Now, in terms of the tension, it might be that residual reddening is actually causing the tension, because obviously the reddening will change the flux and we will see a lowering of the distance measurement in the Hubble diagram. So we select our objects for being not reddened, but we wanted to check to be very, very sure about it. And to do so, instead of using photometric data, which is what we've been doing until now, we went on and analyzed the UV spectra for this sample of quasars. Why so? Because if you look at this Hubble diagram, you see that the black line again is the ΛCDM model. These color stars are telling you how much the extinction should be in terms of the EV minus V parameter for having a shift from the ΛCDM prediction and what we observe. So for the high, probably you cannot see it here, I'm sorry, but for explaining this difference, we need a EV minus V of 0.1 at high redshift. But if we now look at all the UV spectra from our sample and we stack them together, what you see here is our objects are the magenta line here, while the extinction that would be needed to explain the tension would give us a spectra that look like this, so the red-brown one. So our objects are clearly not as reddened as it would be needed to explain the presence of this tension. And another thing we worked on with our spectroscopic UV data is trying to see if our objects are actually average quasars, or if by the fact that we select them for their data quality, we are biasing them in some direction. What does it mean? We looked at them we divided them in redshift bins and also in black hole mass luminosity bins. And then we did the stacked UV spectra for each one of these. And you see here the black line, which is behind everything, is the Vandenberg spectrum, which is the average spectrum for a normal quasar. And our stacked objects never shift from that, regardless of the redshift, of the luminosity, or the black hole mass. So the objects that we're using are not special in any way, they consistently have the same properties at all redshift and at all in all the luminosity range that we're using. So hopefully that now we can trust the fact that the tension with the ΛCDM model is there. We can go on and talk about the very high dispersion, which is the main, still the main issue, because you see here how much more scattered they are compared with Supernovae 1A. So the two things we asked, the first is if we can derive what is the intrinsic dispersion of this relation. Because we do not know the physics, we would really like to, and in order to understand it and also to give reliability to what we're doing, we want to see if we can understand how much the intrinsic dispersion is. And we know there are two things that still contribute to the dispersion, but we cannot remove from the sample with the sample selection. And the first of which is variability. So we know that quasars are variable sources, and obviously, as we are observing them one time in the UV and one time in the X-ray, we are actually watching them at two different physical states. So this produces a scatter in the relation that we are observing. And so the first, to try to estimate how much variability is contributing, we could analyze a subsample of objects for which we have multiple observations, which are only less than 300 out of 2,000 samples, but that's what we have. And so what I'm showing you here is the comparison between two different X-ray observations, and the scatter between these relations, which basically is a one-to-one relation, is 0.09. So the variability contribution is going to be different for different luminosities, because we know that more luminous objects are less variable. But overall, for our sample, we can estimate that this is how much variability is contributing. The other thing that we know is still contributing is inclination, because we know that UV emission from quasars come from the accretion disk. So if we have if it's not, the object is not phase on, we will have a change in the flux that we're observing, while the X-ray emission is thought to be much more isotropic, and so probably not affected, or at least not as much, by a possible inclination. Sadly, we cannot measure the inclination for our object, so what we could do to estimate this contribution was to derive a mock sample of quasars, basically, by starting with this red line here, so assuming a zero dispersion whatsoever in our relation, and then randomly incline our object as we can expect them to be randomly inclined in the sky. So what we get is this scatter here, which has a dispersion of, again, for some reason, it also turns out to be 0.09 dex. So together, these two quantities, these two contributions explain up to 0.13 dex of the residual dispersion we are observing. And this means that the room which is left for the intrinsic dispersion is very little. So we still do not know the physics behind it, but the physical relation between the UV and X-ray emission must be very tight. And this is also confirmed by another work, which is the last one I'll be talking about, that we published last year, in which we tried instead to see how low we could go in terms of the observed dispersion. So we wanted to select the object with the best quality data that we could have to see how low we can get there. And so we selected this subsample at redshift 3. These are objects with a high luminosity, so we expect variability to contribute less. And also they include this subsample of objects for which we have pointed X-ray observations. Our X-ray observations are always from surveys, so we always have serendipitous sources, and having pointed X-ray ones instead really changes the quality of the flux measurements we get. And so for this golden sample here, we find a dispersion of 0.09 dex. Variability and inclination are going to contribute something still, so again, the intrinsic dispersion must be very small. And with this golden subsample now, we can also put it in the Hubble diagram. I'm sorry, the color code changed. But so here you see the yellow ones are supernovae. The green line is again the predictions of a flat ΛCDM model, and this object here lies at more than 4 sigma. And the other thing I want to stress is that for this subsample of object, we also performed a complete, not only the UV, but also the X-ray spectral analysis. So from the spectra, we see no signs of bias or strange features that might affect this subsample. And so the presence of this strong tension is again confirmed. So, final remarks. I hope I have convinced you that the presence of that we can use quasars as standard candles in a reliable way, and that when we do so, we find significant tension with the predictions of a flat LCDM model. This tension cannot be explained by residual reddening in the spectra, which we probe by checking their UV spectra. And when we have very high quality data, obviously we cannot do it for the whole sample at the moment, but for the ones for which we can do it, we can lower the dispersion to lower than 0.1 dex, and this confirms the presence of a strong tension. And in terms of the physical intrinsic dispersion of the relation we are using, it must be very low, and this is something that we need to, it's an important information if we now want to start and try to understand the quasar physics, which is behind the relation that we're using. And with this, I thank you, and I'm happy to
beams with the fluxes, but we have done with the diagram, not the calculated, more sophisticated analysis in which we show actually that the luminosity, both in X-ray and optical, they do show redshift evolution even severely, but eventually when you combine those, it is not affecting the results. So I'm not so sure how much the result that you're showing actually it is being dependent. You see some fluctuation over there. And another point is that if you don't correct for the redshift evolution, practically you cannot apply this relation as a reliable cosmological standard, because you need to correct the luminosity for this redshift evolution. You can either fix the redshift evolution or make it vary, and you can check with Lennart, Bargiacchi, and the time in which we describe this in long detail. So I feel that things missing here. So if you claim the tension, but you have not correct for redshift evolution, I would not trust this result.
thank you.
I have a question. You are not a cosmologist.
Oh?
You say that you are not a cosmologist.
I'm an observational astrophysicist, yeah.
Other questions?
How robust is this relation to modification? Have you looked at the possibility of modifying the relation itself using some additional terms? Or how robust will it be?
In the sense of being not linear, like with higher orders, yeah, there are no significant. Yes, I mean, also the scatter is still a bit high, so probably, I don't know, it could be that there is some significance in an additional term that we are not seeing because the dispersion is still so high. But even for the subsamples for which we have the lowest dispersion, I mean, even here, these are small sample on the other side, but there is an additional term apart from the linear one.
So you tried only powers. Will you try, for example, oscillating terms or something like that?
Oh no, in the sense that in the flux we could try like quadratic or additional orders. Yeah, but
Could you try some oscillation?
also oscillation. Yeah. You mean that the significance of this dispersion is quite reliable in that way.
I have a technical question.
Sure.
About slide, I guess it was 9. Because you say you work with small redshift beats, right?
Yes.
So, I guess just to avoid differences in distances, so that you can
That's the whole point. Yeah.
How large are these beats?
It's very small here, but it's 0.07.
But how do you fix to this?
We took them small enough that the difference in distances, the difference in luminosities that we obtain given difference in distances is smaller than the yes.
Okay. Other questions? Okay. No. So let's thank again the speaker.
Thank you.